In this video, let's take a look at the general multiplication rule for finding the probability of a sequence of events. And so if you look at this formula that's highlighted right here, this is actually just a variation of the formula that you saw in the last video when we were introduced to conditional probability. So instead of the formula beginning with the probability of B given A, it begins with the probability of A and B, but it's the exact same relationship that was captured in that previous formula. Now, in this section, I actually rewrite this slightly. So instead of saying the probability of A and B is equal to all of this, I actually like to think of this as the probability of A then B is equal to the probability of A then multiplied by the probability of B given A. So I'm replacing the word and with the word then to really emphasize the fact that we are going to be working with a sequence of events in this section. Okay, so let's take a look at an example, and when we go through the example, I want you to see that you actually have a number of options for thinking about or for arriving at the answer. And so the example says, among those who apply for a job, the probability of being granted an interview is 10%, or 0.1. Among those interviewed, or I could say given that someone has received an interview, the probability of being offered the job is 25%. Find the probability that an applicant is offered a job. And so the question is saying, let's find the probability that somebody is given an interview, that an applicant gets an interview, and then they get a job offer after having been given that interview. Right? They can't get a job offer without having been given an interview. And so the job offer is conditional upon the interview. Now our formula says one way to approach this is the probability of A then B is simply equal to the probability of A. So that would be the probability of an interview, then multiplied by the probability of B given A, multiplied by the probability of getting the job offer having been given that interview. And we are given both of these probabilities in the description of the problem. There was a 10% chance of getting an interview, and then we can multiply that by the probability of a job offer having been given an interview, which is given in the problem as 0.25. And if we just go over here and say 0.1 times 0.25, we end up getting 0.025. So you could say, if you converted this to a percent, that the applicant has a 2.5% chance of getting a job. Okay, so that's looking at it from a formula perspective. Now let's think about it from a reasoning perspective. So if you think about it from a reasoning perspective, we can also quickly arrive at the answer, and you might even be able to justify why this formula is what it is. So this is saying that you've got a 10% chance of getting an interview. And then it's saying 25% of those people that are interviewed are going to be getting a job offer. So how do we communicate mathematically 25% of the 10% that were given the interview? Well, the word of in math means multiply. So 25% of the 10% that were given the interview would simply be 0.25 multiplied by 0.1. And so from that reasoning perspective, we also arrive at that answer of 2.5%. And you can see that the reasoning perspective is completely consistent with what the formula was doing. You can see that we were taking the product of the two probabilities. Okay, so we've seen that you can use a formula. You might be also able to reason through the problem. And then the third approach that I want to show you here is that you can use a tree diagram in combination with the formula to have a really nice visual of what's happening. And so a tree diagram would look something like this. So in the beginning, you are either given an interview or you are not given an interview. And the chance of getting an interview is 0.1. So I'm just going to indicate that with 0.1 along this line segment. And then the chance of not getting an interview would be 0.9. Okay? This tree nicely captures conditional events because anything that happens in these branches of the tree are conditional upon this particular event happening right here. And so you've been given an interview. Now you are either given a job offer or you are not given a job offer. So I'll say not given a job offer. And the probability of getting a job offer, having been given the interview, we saw was 0.25. And then therefore the probability of not being given a job offer would have been 0.75. And so if you provide yourself this visual and then you want to say, hey, I want to know what the probability of eventually getting that job offer would be, then you would have to go all the way down this part of the tree. You would need to be given the interview, and then conditional upon that interview, you would need to be given that job offer. And then what we would do is just take the product of these as we've seen in both the formula and in the reasoning approach. So you would do 0.1 times 0.25 and once again arrive at our 2.5%. But the key thing here that we're starting to see is this, that to compute the probability of a sequence of events, and in this case we're seeing that the event B is conditional upon event A, but to compute the probability of a sequence of events, we are multiplying the probabilities of those events. Okay, so that's the big theme that we're beginning to see right away here. Now what we're going to do is we're going to take a look at events that are sometimes independent. And that's because we don't always have event B being conditional upon event A. And I want you to see what happens in that type of a setup. So two events are considered independent if the occurrence of one event doesn't affect the probability of the other. So the first thing that we're going to do here is just practice this a little bit, and then we'll take a look at some examples with all of this material a little bit later on. And so this first one says, let's decide if the events are independent or dependent. I'm rolling a die and getting a 6, and then rolling a second die and getting a 3. So is getting a 3 on that second die impacted by getting a 6 the first time around? Absolutely not. Getting a 3 on a second roll is not impacted by what happens on the first roll. And so as a result, since the probability of this event is not impacted by the probability of this one, we would say that these events are independent. Example B, drawing a card from a deck, not replacing it, and then drawing a second card. So if you do not replace that card after you draw it from a deck, then the probability when you're drawing a second card is going to be impacted because you began with 52 cards in the deck and now you would only have 51. And so as a result, you would say that these two events are not independent, or we would say that they are dependent. Okay, example C. Drawing a card from a deck and getting a queen, but then you replace that, and then you draw a second card and you're looking at maybe the probability of getting a queen. Well, if you replace that first card, then aren't you back to where you started from with the probabilities with the second card? And so the probabilities of getting a queen the second time around are completely unimpacted since we replaced that first queen that we would have drawn from the deck. And since the probabilities of that second event are not impacted by what happened the first time around, we would again say that we have independent events right here. In example D, I said selecting a lottery ball from a tumbler, not replacing it, and then drawing a second ball. And so there we are again with the idea of not replacing it. So if you don't replace it, and then you're drawing a second ball, then the probabilities when selecting that second ball are definitely going to be impacted since you did not replace that very first ball. And so once again, this would be an example of dependent events. So one of the big themes that I want you to notice just going through these few examples right here is that when we talk about replacement or with replacement, then that is going to be associated with independent events. And that is because when you replace a card or you replace a ball from a tumbler or something like that, then you're going back to your very original situation. And so your probabilities the second time around would not be impacted by what happened the first time. So with replacement, I'll add the word with there, with replacement is associated with independence. And then If you are not replacing, or I can say without replacement, that is going to be associated with conditional probabilities or dependence. And that is exactly what we just saw when we looked at a couple of these examples right here, because again, if you don't replace, then the probabilities of that second event are going to be impacted. Okay, now what are the implications for us in this general multiplication rule? Well, let's take a look at our formula once again. So we had the formula probability of A then B was equal to probability of A multiplied by the probability of B given A. But again, this was with conditional probabilities. But when event B is completely independent of event A, then the probability of B given that A occurred is simply the probability of event B. So we end up with this formula. The probability of A then B is equal to the probability of A multiplied by just the probability of B. And so the theme is still the same. To find the probability of a sequence of events, A then B, whether you have conditional events or dependent events, or you have independent events, what you do is you take the product of the probabilities for each event. That is a major theme that I want you to recognize in this video. Whenever you're doing the probability of a sequence of events, take the product of the probabilities of each event to get your end result. Okay, in the next video, I'm going to take a look at some specific examples that apply exactly what we've been seeing right here. So check that one out now. Thanks a lot.